All right, good afternoon. Let's get started. Hope you all had a good break, right? Long spring break. Right? I already forgot what I'm supposed to teach, right? Hope you all not forgetting what we learned before the spring break. All right. So there are homeworks, due this week, right? So before the spring break, we talk about mainly about the beam stress. So in a beam, here is a quick review. So in a beam under loading, it can be a distributed load, country force, or a bending moment, right? So you're going to have, in general, you're going to have a bending stress. That's a normal stress in a beam, and also a shear stress. And here are the equation to calculate, right? So we talk about how the stress is distributed inside the beam. So here is a quick quiz for you. Okay. So for this beam, right, you have this 4-point bending. All right. So you're going to have shear force in the beam. So therefore shear stress, and also they're bending. So there will be a bending stress in the beam. So quickly, without calculation, can you judge where is the point that has a maximum stress? For example, for the bending stress, where is the maximum bending stress? The 6 point, A, B, C, D, E, F. Which part? Give me an answer. Which one? Where is the maximum bending stress? D, right? Or F. They're the same, opposite direction, right? Same value. So D and F. Okay. Why not C and A? The bending moment is smaller at the A and the C, at the location, this cross section, ABC cross section, right? So remember the beam, the VM diagram, right? If you draw the VM diagram, that's the M. So in the middle part, you have the bigger M. Here, the moment is half of it. So here, moment is bigger. So therefore, the stress here will be bigger, right? But it must be at the edge. So that's why you have answer D or F, or D and F. Okay, what about shear stress? Where's the maximum shear stress? A and B? What about A? What's the shear stress at point A? It's 0, right? And the top edge, bottom edge is always 0. So it can never be at the A or D or C or F. So that's impossible. It's always 0 there. So the only possibility is B or E. Now, what about the E, point E? What's the shear force at the E? Shear force, V. What's the shear force at this cross section, DEF? It's 0, right? So therefore, there won't be any shear stress in DEF. So the only answer will be point B. Remember the shear force diagram? So the shear will be going up and then coming down, 0, and then going down and then up. So here 0, V. So V equals 0. How can you have shear? Tau must be 0. Right. Okay, so now go back to your note. Review all this content because this all will be covered on next exam that's coming up Monday. Right. So the coming Monday we're going to have our second exam, and that will be on the torsion, shear, and M, shear force, bending moment diagram, and also the bending stress and shear stress. Okay, so for that, actually, I have here a summary sheet. It's more like a formula sheet for you all. So let's look at that. So I'll do a quick summary about what we already learned. That will be covered in the next exam, right? So first part is a torsion part. Okay, so we say torsion is pretty much very parallel to the stretch, right? Lots of equations that are parallel, the theory, the concept are parallel. First, deformation, equations are similar. But now it's a twisted angle, right? We did a summary after chapter 3, but here just refresh your memory, all right? So the twisted angle, and then how much is the shear stress in the beam, in the inner shaft when you twist it. So the edge will maximum in the center will be 0. So the shear stress distribution will be a linear distribution depending on rho, right? So that's this equation given here. So this equation here, tau equals to T rho over IP. And then what's IP? So that's the question here, right? And then if you have a series of shaft, non-uniform shaft, then the total rotation angle will be all them add together. So that's determinate situation. If you have a shaft that fixed between two rigid walls, you're twisted in the middle, then it's become indeterminate. And for indeterminate, same trick, the Fed.com, right? You're going to use that again. So the compatibility will be the relation between all these angles, how they related. And we had a couple of homework problems and examples in the class as well. So that's the part based on what we had last exam, right? That will be the challenge part. So making sure you can solve the indeterminate problems if it come up. All right. Then we talk about the stress in a shaft. That is, when you look at the cross section, there are only shear stress. But if you cut an angle, not perpendicular to the actual direction, then you're going to have both normal stress and shear stress. And that normal stress will be maximum at 45-degree direction, right? When you cut a perpendicular, cut a cross section, the normal stress will be 0. But if you cut 45, that's where the normal stress becomes maximum. So again, here the 45-degree, the special direction. All right, and then we had the equation about strange function and the strange density. So that just equation will be on your formulation, right? Okay, so that's for chapter 3. And then we spend a lot of time talk about the VM diagram for beams. Right. So we talk about 3 types of beams: a simple beam, or cantilever beam, or overhanging beam. So this is the 3 basic type of beams. Okay, you need to know how to find the reactions, and that's the key part, right? If you get the reaction wrong, everything will be wrong. So get the reactions. The reaction include a moment or a force, depending on what kind of restriction, right? So if you have a pin support, the only reaction force. If it's a fixed end, there will be reaction force and the bending moment, right? Okay, so then when we talk about the load, we talk about distributed load, concentrated force, or concentrated movement. That's the 3 basic type of load we deal with. Actually, in the textbook, they also give you if there is a distributed movement. You're going to calculate. That's the same, similar thing, right? Okay, so for the VM diagram, we talk about you can make a cut, draw the VM diagram, or you can just use the 7 rows, follow this road, and you can just directly draw it without the VM diagram. So the reason we do this way is because this way is quicker. Right? You don't have to make a cut to kind of a little bit quicker. For the exam, if you really, really want to make the cut and find out the movement and then draw it, that's okay, but that's be much slower, right? If you do this way, it's much quicker, and definitely you're going to have enough time for solving the problems. Okay, so there are 7 rows there. I may not go explain one by one, but the key thing I want to point out is how the area are related, right? The area V will be the M change, right? And that's one relation. And also, if there is a concentrated force, only force jump, the shear force jump. If there is a concentrated moment, only moment jump. So there are no cross-talking between force and moment when you draw the VM diagram. Right? So that's the 2 key points I want to bring up. And those already posted, so you can review it, get familiar with this sheet, and then so this will provide to you during the exam, right? But you need to know what all that means there. You don't ask me to explain what that means. Right? So if you don't understand which part that's not clear, you can ask me now or during my office hour before the exam, but not during the exam. All right. So that's the part, and then the last part. Okay, the last part is this chapter we just covered. So that's the beam stress. All right. So in a beam, you're going to have normal stress. That's the equation. And then you need to figure out how to determine the maximum. Most of the time, we care about the maximum. We're not care about the distribution because we know what kind of distribution, linear distribution, right? But we care about the structure. A beam is strong or not strong enough. So therefore, we need to find out the maximum stress. Right. So here are the equations for maximum normal stress and maximum shear stress. Right. And so here, the next line, second line, actually give you how to calculate the section modulus S and the moment initial I and also the shear component Q maximum. So those are the equations. So the second line basically is the geometric function, right? So you just need to know for cross section that's rectangular or for cross section that's circular. So that's just basically the two types. You know how to calculate. So the basic equation is the first line. So you have the sigma maximum, tau, and tau maximum. Okay, so that's basically the content we covered since exam 1. And that will be on exam 2, the coming up Monday. Okay, any questions? And again, this formula sheet will provide to you during the exam. Yes?
The homework,
I think the homework is supposed to be due this Wednesday, right? This Wednesday, yeah. The Wednesday, that's the beam stress part. So that will be on the coming up exam. Yeah, so but I'll post the solution after Wednesday night, so then you can see it there. So if you need, you make a copy for yourself, right? We don't have enough time to turn around to give back to you. Yes, thank you. All right. Okay, any other questions? All right, so I'll be available most likely this Friday as well. So today after class, Wednesday after class, and Friday after class. So if you have questions, feel free to stop by during my office hour. All right. Other questions? Okay, any other questions? All right, if not, we'll move on to talk about new content, that is beam deflection. So it won't be in this exam, but it will be in our next exam. Right? Remember, so far we talked about the load in a beam, and then you determine the internal force, that's the shear force, bending moment. And then we calculate the shear stress and normal stress, so stress. But we haven't talked about how does a beam deform? And here it is. So we'll need to figure out when you're applying certain load, how much does a beam deform and what kind of deformation you're going to get. And that's what we call deflection. So the deflection of a beam, that's what we're going to cover. Okay, why do we call it a deflection for a beam? Because when you deform beam, you're bending it, right? So the load is lateral, and therefore the deformation is lateral, right? So it's a lateral displacement, therefore we call it deflection. So by deflection, we basically mean how much will the beam move laterally. We don't care about this axial, because axial we talked about in chapter 2 already, right? Elongation or shrinkage, we'll talk about that. So in this case, when you have a beam, you bend it, like we show here, you basically get a lateral deformation or displacement, and that we call a deflection. And we use the letter V to represent it. All right. Okay, so now how can we determine the deflection V for a beam? All right. So what do we already know so far? We know if you have a beam right? So we know how to determine its stress, right? Okay, so to determine the stress, remember when we try to determine stress, we made some assumptions. Right? How did we get the stress? Basically, that's my question. Do you recall how did we find out the stress in a beam? We made assumptions. We assume, right, how the beam is going to deform when you bend it. So we based on some geometric, pattern, deformation pattern. Then we determine how does it deform, and then we find out the stress. See, we already talked about how it deform, and then we get the stress. But back then we just quickly went over without saying how it actually deformed, the detail. Right? Okay, what the assumption we made when we tried to determine the stress? Plain assumption, right? We assume when you bend the beam, the parallel cross sections, when you bend it, will turn, but remain as a straight plane, right? So remember that. So if you look at the beam, this is a block of beam, right? So when you apply a bending moment, it's going to deform into this shape, right? We assume this plane here will remain as a plane. This will remain as a plane, right? And then we say, oh, this will deform. So there are neutral axis somewhere, not stretched, not compressed, right? And that line, we call it the neutral axis, or neutral plane. Then with that, we say, okay, see here's the center. So this will be, we call it a rho. Okay, what's a rho? The radius curvature. We say, oh, you are bending, so therefore somewhere there must be a center of the curvature. And that point from there to this part, we call it rho, right? And actually we find out if you apply a moment m here, see this is a moment m. Okay, what's the rho? Do you recall the equation? M over EI equals 1 over rho. Anyone remember this? Right? So we actually find out what's the rho. And that when we try to get the stress. So we just pass by it without saying that's actually the deformation. This is deformation, right? Because we know if you can determine when you apply moment m, what's the rho, then you know how much it deforms. Because initially it's a straight tube, a straight beam, and you bend it into a curvature of a rho. So that's a deformation, right? That's a deformation, right? Straight initially rho equals what? When it's straight, infinity, right? So 1 over rho initially was 0, and now after you make the deformation, you have certain value and given by this equation, right? So imagine you have a beam, okay? So as I think this one show here, okay? So for this beam, when you apply a moment, then it will deform into this shape. So you're going to have a rho here. So this will be the rho, right? So if I can find out the rho, then maybe I can get the deformation. Okay, so that's the idea, how we're going to follow to find out the deformation. Okay, now the question is, what's rho? Okay, what I want to find out is, okay, when I bend this beam, what's this Vx looks like, right? I want to find out the V. How much is the deflection? How much this beam, the central line, move away from the initial straight line, right? That's what I'm looking for. Okay. But now I already know we have this relation. Okay, so is there any relation between the deformation Vx and the curvature rho? Yes, we learned something in calculus, right? How do you determine the curvature of a curve? If I have a function, say y equals yx, okay, what's the curvature of this curve? Anyone recall that? Good memory? Something related to derivative, right? Y prime or y2 prime. Okay, so let me write down here. So the curvature k will equal to y1 prime, and here y2 prime, 1 plus y1 prime squared. That's the equation we got. Does this look familiar? Somehow, right? Have some impression about it. Right? Okay, if you're not, go find your textbook, right? So after this one, search online or textbook. Okay, make sure this one is correct. So you accept it. So for now, we take it for granted. This will make it easier. Okay, so we assume this is the correct equation. So say Dr. Han is writing this correctly. All right. Okay, so if we know the curvature, the curve function yx, then we can find the curvature by this equation. All right. Now, for this case, I'm trying to find this Vx. So what's the curvature of this curve Vx? Should that be k equals to Vx2 prime, then here square root 1 plus V1 prime squared, right? Vx is the yx we had before, right? Because the curve now is Vx. Okay. Now, what's k? K equals to curvature. It's 1 over rho, right? That's the definition of curvature. Right? So 1 over r is the curvature. So now here 1 over rho is the curvature. Right? Okay, so now we have the equation. Right? So let me use the next page just to write it down here. Okay. So this here actually I have this one. This is a derivation showing why that is true. Okay, why 1 over rho is curvature. Because here, if you look at this distance here, ds is supposed to be rho times d theta. So this angle called d theta. Okay, that's just a quick explanation. All right. So therefore, you have this 1 over rho equal d theta ds. Okay, what's d theta ds? It's curvature, right? This, right? What's d theta? It's a slope, right? Now, from here to here, what's the jump here from this equation? Okay. So according to this equation, you should have this relation, right? Let me just square this one. Okay, that's a general rule. Right? So you have a y square, y prime square, or the v prime square at the bottom. Okay, so this looks complicated. Now remember, we're talking about small deformation here. So for small deformation, what's the v prime? Should be small. Now a very tiny thing, you square it. It's a high order, even smaller, right? So therefore, you can actually throw away this term. So from this equation, you actually get 1 over rho equals to V2 prime. Right? So that's mathematically you get this one. Okay, so next slide, here explain, physically kind of give you an explanation. All right, so first you have this 1 over rho equal d theta ds. Now what's d theta? Or d theta ds? Slope, right? So that's the slope. So therefore you have, I think it's here. Okay, so tangent theta should be equal to that. Okay, what's tangent theta? It's theta. Because tiny angle, small angle. So you combine, okay, so you get theta equals tangent theta, right? So this ds basically is dx. So what do you put this back to this equation here, into this equation. Now what do you get? Okay, let's see what you get. You get this equation, right? So theta, basically the angle is the slope. First order derivative of v is the angle. You say, oh, this should be here. This should be dv dx supposed to be tangent theta, right? Based on our definition from calculus. Right? But what's the tangent theta? Well, tangent theta is theta. So you have theta equal dv dx. Right? Okay, now put this one back into the previous equation. This, what do we do here? So you get this relation. Okay, now take the theta here. So d theta dx equal that. Okay. So remember, we had this equation before, right? So now theta, this one you determine is here. So you take it in, they give you this equation. All right. So it's a mathematical, equation. You just replace one another, and use it. Remember, theta is small, so that you get this. Okay. So with this equation, now remember we already have rho equals to m over ei, right? So therefore, you put it in together. That's what you get this one. Right. Or sometimes you can write this way. So v second order derivation, right? So you can write v2 prime. That's what v2 prime means. Second order derivative. Okay. Well, somehow now we have an equation about the deflection v. So the deflection v, okay, we don't know it, but it's the second order derivative of this deflection v equal to m over ei. Right? So this says if you know m, then you can find out v. How? You basically solve a second order differential equation, right? Okay, in EA1, EA2, we talk about solving differential equations. Now here is a use of it. So what you learn is useful here, right? So we have a second order derivative equation, differential equation here. Okay, so therefore this part, okay, this chapter determining the deflection is pretty much a mathematical exercise of solving differential equations. Because we see here the derivation, all right, of the deflection is a differential equation to m about it, right? Okay, now can everyone solve this equation? Recall what we learned from EA1, EA2, right? If I know m, can you solve this equation? Yes? How do you do it? We learn quite a few things. Separation of variables, right? That's one way. If you have multiple variables. Now, how many variables do you have here? One, only one, Vx. V is a function of x. It's a single variable, x only. So therefore, there's no need for separation of variable. There's no t involved. It's not dynamic equation, right? So you don't need the separation of variable. It's just an ordinary second order differential equation, right? It's like I give you y2 prime equals to, let's say ax. Can you solve this equation? Integrate twice. Similar here. This one means v2 prime equals to mx, and then ei, let's say it's a constant. So this is a constant, like the a. Now, can you solve this equation? Yes. We just integrate twice. You'll get the answer, right? Okay, so let's go through this process by using examples. I think example will explain better than just give you boring theory how to solve this equation. Okay, so the first one, I think it's here. Let me see here. Okay, let me go back here. I want to go through example before we go other part of theory. Okay, let's go through this problem. This one. If you have a beam, okay, so maybe I'll just draw a new page here. Okay, let me go down, draw a new page. Okay, so I'll use this page. Let's see. Okay. Oh, that's one. Okay, so I just need to insert a new page. That's it. Okay, so we have this page. So the first example, we start very simple, very simple example. Okay, here's a beam. Oh. All right, so here's a beam. Oh, what happened? To allow me to write down somehow. Sorry, let me just go there. All right. So we have a beam. All right, very simple situation. Okay, give a length. 5 meter long. Okay, 5 meter long. And then we know the cross section, so you know the E and I. All right. So we say it's a number we know. All right. So now this one I apply moment. Let's say M. And M here, a pair moment. All right. Okay, I want to find out when I apply moment. Let's know. Let's say give a value. 10. All right, 10 Newton meter. All right. So when I apply this 10 Newton meter to this beam, okay, how much deflection I'm getting in this beam? Or what's the maximum deflection? Let's ask the maximum, right? We want to find out this beam. When you're bending, how much the maximum deflection? Initially, it's a straight line, right? A straight beam. So this most likely will deform into this shape. So we want to find out what's the maximum. All right. Okay, how can we find the deflection V? Let's say at any location, this will be Vx. Okay, how can we find the Vx? Use the equation, right? We just got this equation. So V2 prime equals to mx over EI. And EI we know is a constant. Okay. So we know M. So this will equal to what? 10 over EI. Is that correct? Okay, now can we find the V? If I can find the Vx, then I know the deflection of any point. X can be any value. Then I can find out the maximum easily, right? So the key question is basically find the Vx. Okay, can we solve this equation and find out the V? Okay, tell me what to do. How to find the V from this differential equation, second order differential equation? Integrate, right? Okay, let's integrate. Integrate this one, what do you get? So integrate, you have to do integration on both sides. So on the left side, if you integrate once, what do you get? Will be 1 prime, right? Right? Okay, then equals to, on the right, integrate. So it will be 10 EI, that's a constant. That's like the A, right? Times X. Plus a constant, right? Plus a constant, I call it C1. Is that correct? Yes, that's according to our EA1, EA2, right? How to solve a second order differential equation. Okay, integrate once, we get 1 prime, but that's not our answer. What are we looking for? V. Okay, how can we get the V? Integrate one more time, all right? Let's do it together. So V itself, we integrate. So integrate this part will be EI 10 X integrate will be half of the X squared, right? Okay, then plus C1 integrate, C1X plus a constant C2. Oh, we find out the V. So this is the Vx. Now we have it. But so can I find the V at any point? Let's say x equals 2, x equals 2.5. No, I cannot yet. Why? Because C1, C2 I don't know yet. So integral constant. I need to find out C1, C2. Right? Remember when you solve differential equation, you do the integral and you get the integral constant there. Okay, how do you determine the constant? Boundary conditions. Okay, where is the boundary? The boundary will be here. X equals 0. That's a boundary. Here, x equals 5. That's a boundary. Okay, now at x equals 0. What's the boundary condition? What's V?
0.
V must be equal to 0. So V at 0 equals 0. Okay, that's one boundary condition. Okay, I have two constants there, C1, C2. So I need one more. Boundary condition. X equals 0. Already given. X equals L. X really equals 5 in this case, right? At x equals 5, what do we have? V5 equals to, what's V at x equals 5? 0. Okay, so 0. Now we have two conditions. So we can use this to determine C1, C2. Okay, now let's plug in. So you find the C1. Okay, use the first one. So you have V when x equals 0, right? So that equals 0. And that equals to this 10 EI, since the first one, I'll write more detail. So V0 squared over 2 plus C1, 0 plus C2, right? I just plug x equals 0 in there. Okay, what does this one give me? You get C2 equal to 0, right? Okay, so we know this will be 0. Now, use the second condition, second boundary condition. So you have 0 equals to V at x equals 5. So you have 10 EI, and then 2, that's 5 squared, plus C1 times 5. Then plus this one, we say we already know C2 is 0, right? So it will be equal to 0. Okay. Now can we find out C1? Yes, we can find C1 from here. So C1 equals to negative 10 EI, right? And then this will be 5 over 2. 5 squared over 5. So that's 5. Right? Right? You still have 5 squared over 5. So that's it. So it's basically, or you can simplify one more step if you want. 25 over EI, negative. Okay, so now we have this V. So Vx will equals to, we know it, 10 EI x squared over 2 plus, actually minus 25 EI over this part x. Right? You all agree? Okay, so we find the V. Now, can you find the V maximum? How do you find the maximum? Suppose to be from here, you can go V prime x equals 0. That gives you the location x. Okay, but this one, do we already have it somewhere? See here, we have it here. Right? So you let this one equal 0. You determine the x. Right? C1 we already know. So what's the x when this takes 0? What's the x value when V prime equals 0? $2.5. Right? So if you do the calculation, it will be 2.5. Okay, visually now it's 2.5 reasonable. Yes, because you are bending, so this is symmetric, right? So moving down, therefore the maximum must be in the middle because it's symmetric, right? Okay, so we know the 2x equal 2.5 is correct. Okay, now what's the maximum value? The V maximum. Can you calculate it? Yes, by let x equals to 2.5. So you put x equal to 2.5 here. Okay, this will be 2.5, and this is supposed to be 2.5. Put it there. You calculate it. All right. Okay. Let's do it together. See what's the value. Okay, so that's supposed V maximum. Oh, let me just write down here. V maximum equals to 10 EI, right? Will be 2.5 squared, and then over 2. Then minus 50 EI. What's the 50 EI? 25 EI. Okay, so 25 EI, and then times 2.5, right? You put x equal 2.5 there. Okay, anyone can simplify this one? How many EI there? Anyone got a calculator? Or we can just simplify it. Okay, I don't have a calculator here. Let me just say if I can simplify it. So I put a 2 here. Okay, so 2, this will be times 2 here. So I have 2 EI. Then inside will be, this will be 62.5, right? 62.5, and then minus 5 times 25. Is that correct? So it must be a negative value. Is that correct? Negative value? Yes, because it's moving down, right? When you're bending, you're moving down there. All right? Okay, any questions here? I think maybe more, leave the time for questions other than get the actual number. Yes?
Doesn't that say positive, factor into positive?
Yeah, so here is the sign convention. Remember, we talk about this all the time. When you have a bending, right? This pair movement, when you're bending this way. So when you have a cable here, right? So if I bend in this way, so that's a positive bending. So the moment is positive, and the deflection, we say, you go this way. So that's a negative deflection, you're going downward, right? And if you bend in this way, we call it negative bending, and you're going to have this going up, so they have a positive V value. So V value always, when positive M, you have negative V. When you have a negative M, you have positive. Right? That's why there is a negative sign there. All right. Okay. We don't have time to cover another example, so we'll continue next time. So I leave there are a couple of minutes. So any questions regarding to previous chapters or what we learned today? All right, if no question, thank you. We'll stop here.